afternoon. Thank you all for coming to the second ECE-IISc-Distinguished Visitor Program lecture. This Distinguished Visitor Program has been instituted at the Institute by our own ECE department alumna, Nirmala Govindan, who's there right here in the... So let's acknowledge. So the first one was given by Professor Athina Petropoulou, who's the president of the Signal Processing Society and distinguished professor at the Rutgers University. And we are very fortunate to have Professor Maria Greco to deliver the second one. So I just wanted to welcome you and thank the donor, alumna, Nirmala, who happened to be my master's project student also in '96. So that is a good connection. So now I would like to invite Professor Devdeep Sarkar to introduce the speaker.
Yeah, thanks very much, Professor Hari, and I am Devdeep from ECE department, and I am welcoming you all to this ECE-DVP lecture, which is going to be delivered by Professor Maria. So let me read out her bio. So Professor Maria Sabrina Greco graduated in electronic engineering in '93 and received the PhD degree in telecommunication engineering in 1998 from the University of Pisa, Italy. Her general interests are in the areas of statistical signal processing, estimation, and detection theory. In particular, her research interests include clutter models, coherent and incoherent detection in non-Gaussian clutter, CFR techniques, bistatic and multistatic active and passive radars, cognitive radars, I think, which is going to be the focus of today's talk, and integrated sensing and communications. She has authored many book chapters and more than 220 journal and conference papers. From December '97 to May '98, she has joined Georgia Tech Research Institute, Atlanta, USA, as a visiting research scholar, where she carried out research activity in the field of radar detection in non-Gaussian background. In '93, she joined the Department of Information Engineering of the University of Pisa, where she is a full professor since 2017. In May to June 2015 and in Jan to Feb 2018, she visited as an invited professor in University of Paris Sud in Paris, France. Professor Sabrina is an IEEE fellow since Jan 2011. She was co-recipient of the 2001 and 2012 IEEE Aerospace and Electronic Systems Society's Barry Carlton Award for Best Paper published on the transaction of AES, and co-recipient of 2019 EURASIF JSP Best Paper Award, co-recipient of H. Maimno Award for the Best Paper published in A System magazine, and so on. So I think she has also received the Exceptional Service Award for Exemplary Service and Dedication and Professionalism as EIC of the IEEE AES magazine. And she has been General Chair, Technical Program Chair, and Organizing Committee member of many international conferences over the last 15 years. She has been the lead guest editor of many journal special issues on radar signal processing. So the list is pretty long, so I will not take too much of your time and maybe go directly to her lecture. And just to close the introduction, she is now the President-elect of IEEE AESS 2022-2023 and will assume the position of President of IEEE AESS on 1st Jan 2024. So with that introduction, I will like to invite Dr. Sabrina for the lecture. The stage is all yours. Thank you.
Hi everyone, welcome to this talk, and thanks for the very nice introduction. So the topic of this talk is on cognitive radars. And I will start from the beginning, so I will introduce the concept of cognitive radars. The concept also its foundation, because it is true that it's a new concept, but it has some foundation in old techniques. Then I will show you some application and some example, in particularly spectrum sharing in radars, the tracking in passive radars, then the beamforming and massive MIMO radars are all based on different level of cognition. And then at the end, I will draw some conclusions. So let me start with the definition of cognitive radar. It's a IEEE official definition. So a cognitive radar is a radar system that in some sense displays intelligence, adapting each operation, each processing in response to a change in environment and target seen. In comparison to adaptive radar, cognitive radar learns to adapt operating parameters as well as processing parameters and may do so over extended time periods. So the most important part of a cognitive radar system is the ability to learn, to adapt the operational parameters, and to learn over time. So you will see how this concept of learning over time applies to different levels of cognition. The concept of a cognitive radar has been introduced by Professor Simon Hyken in a famous article on the IEEE Signal Processing magazine in 2006. At that time, only the concept of cognitive radio was already popular and well known. So in some way, the roots of this cognitive radar idea comes from the cognitive radio. But there is much more. Because the foundation of the cognitive radar, and for instance, in the sensor management paradigm, where you adapt what, for instance, in the tracking, a radar can repeat the transmission on the same target in order to be sure that the target is there. So in some way, it learns from the environment that there is something and it repeats the transmission to be sure about it. There are other things in the sensor management paradigm. Waveform diversity. I remember that when we started working at the beginning of 2000 on waveform diversity, our idea was to design a system that was able to change on the fly the transmit waveform. Well, all these concepts nowadays are under the framework of cognitive radars. So you still have the cognitive sensor management paradigm, the waveform diversity, and also the knowledge-based systems. Knowledge-based system has, in some sense, the basics, so where we build the cognitive concept. So let me explain in this very easy cartoon the difference between a classical conventional radar and a cognitive radar. So the conventional one is only this upper part, and you see that there is a dynamic model environment, so it can be the clutter, can be the interference, there are moving targets, or there can be also communication systems that interfere with the radar. There can be jammers and so on. Here we have the sensor, so this is the radar that perceives the environment, so both the target, the interference, and the clutter, and whatever it is in the environment. Then, of course, there is some signal processing, a lot of signal processing, I should say, to retrieve the characteristic parameters of the target, so to detect and track the target based on the observation that is generally very noisy. And then we learn something so we can update our database on different kind of targets, for instance. But you see there is no any feedback between the transmit and the receive. So the knowledge that the radar learns is not used to change the parameter on transmit. Now look at the bottom part here of this cycle. This is typical of the cognitive radar. you see that there is a feedback between the receiver and the transmitter. So this is action. It means that the radar, based on the knowledge, based on the observation of the environment, is able to change the transmit parameters. So it's able to change the beam pattern, even to select different antennas, to change the waveform. It could be also able to change the position of the sensors here and there. So there are many options in that sense, and you will see some application. So this perception action cycle here, that is, this is typical of the human cognition, and this is typical also of all the cognitive systems. Now, the first step, as I told you, was the cognition knowledge-based sensors. So you see here that in a cognitive radar, you have the typical adaptivity on receive, because the majority of the radars, modern radars, are adapted on receive. So it means that they process in adaptive way the signal that they receive in order to detect or to track or to classify the targets, so the object that they observe. But there is no any adaptivity in the adaptive radar on transmit. So they have the waveform that they have. They have a specific rule for detection or for tracking, and they don't change them. So in the adaptive radar, this is the state of art, but in the cognitive radar, there is this more step. There is the adaptivity also on transmit. So you can change all the parameters. You can manage in a cognitive way all the resources that you have, and you can also change the way the radar itself acts based on the knowledge that you learn from the environment. Now, let me show the comparison between the human capability, human cognition capabilities, and the capabilities, the technology, the technical analogs and the cognitive capabilities of a machine, so radar, for instance. So this is the Bloom's taxonomy that is famous. I'm not inventing anything, and this characterizes the human cognition abilities. And going from the bottom to the up, then you see remembering, understanding, applying, analyzing, evaluating, creating. Of course, the creation is the maximum cognition ability of the human being. Now let's look here in a red. In a black, you see the explanation of these different capabilities, human capabilities, and in a red here you see the technical analog, so something that mimic the human capability. Then for the remembering, of course, we can have some database where we can put all the information we have. For the understanding, so constructing some meaning from the data, so from classifying, identifying, selecting, then we can use this, the machine learning, different level of machine learning, also actually statistical signal processing, so extracting parameters, understanding what we are observing. Now applying, so use information in new situations. This can be done through the knowledge-aided adaptive processing. But we want to go up, so we want to use new technologies to make the radar system or a machine able to analyze, to draw connection among different ideas, and then justify and also defend or the decision taken by the system itself, And this is really the most difficult one. So not only dealing with new situations that we have not seen before, but also creating new things. So new ideas, new concept that only the human being is able to do, and a machine is not able yet to do. Now, let me explain how this concept of cognition can be applied to a radar system. You see clearly that in this figure that is not mine. I borrowed this figure from an article appeared in 2018. I like it because it's clear, and you see here that there are 3 different levels of cognition and sophistication. Here along the x-axis we have the degree of decision sophistication, and here of the planning sophistication, and here the degree of memory. So the first level of cognition, so using the adaptivity on transmit, is that cube here. So it's the minimum level of cognition. But if you want to make really fully cognitive radar, you need to go towards this cube that is here. Now let me explain what is on this axis. So let me explain the degree of decision sophistication. So the first degree, you have fixed rules. It means that you have a specific criteria that your system applies. And for instance, a comparison with a threshold. So every time your observation is greater than the threshold, then you have a detection. That's it. That's a fixed rule, okay? But then you can make a more sophisticated decision, learning from the environment the rules. So learning the policy of decision over time. Then you can use some heuristics, learn from the environment, and then the last level is the optimization. So based on the observation of the environment, you start from fixed rule, and then you optimize the rules itself, okay? Now let's go to the degree of memory. Memory at the beginning is fixed, means that you have a database that you can use, for instance, for classification of the targets. In the next level, you have the external knowledge. So you learn from the environment, but also from other sensors, so from the observation of other sensors. So you improve your database. But you learn. It means that when you are able to extract the information from your database, you are able also to classify objects that are not in your database. So that's the learning, okay? Now let's go to the level of sophistication in the planning. You can be myopic or non-myopic. Myopic means that you plan only the next step. So you don't have a plan for the future. And then you do what is best for the next time instant. It doesn't mean that this is the best choice on the long run. So if you do planning, if you plan something, then you are non-myopic, and you are able to improve the performance when the observation time is long. So you see, going from the first step, when the ruler fixed, the memory is fixed, and you are myopic, to the last level, when you are able to extract information from your memory, when you are able to optimize the rules, when you are able to plan future moves, then you are really fully cognitive. So there is a long way to go from the fully adaptive to the fully cognitive, but we are already applying some of these techniques. So let me start with the first step. The first step is quite popular nowadays for what is called the spectrum congestion. That was the idea at the beginning. And you will see that we applied something similar to what the cognitive radio does. And this is still the first level of cognitive radar. So this is fully adaptive. It means that the system actually doesn't learn over time, long time, but adapt the transmit parameters based on the observation. So there is a feedback between the transmit and receive, but there is not a real learning or real cognition. So imagine that there are multiple sources in the same environment. They transmit their waveforms. They can be other radars. They can be communication systems, typically communication systems. And actually the radar is a secondary user and the communication system are the primary users. It means that they have the right to occupy the bandwidth, and the radar has to wait until the specific channel is empty to transmit. Okay, so this is this scenario. So you see in this cartoon that there are multiple channels and in multiple time slots. The primary user are the gray ones, so they are occupying a specific frequency band in a specific time slot. And the green slots are the spectrum opportunities. So it means that in that specific time, in that specific frequency, you have an empty slot, and the radar can transmit in that specific channel. This can be a radar that is transmitting in that specific channel, or can be also on an FDM radar, so with multiple carriers, and then it's trying to transmit in one of these carriers that is free. So you can imagine that the first mission, in this case of the cognitive radar, is to sense the environment, to sense the spectrum, and to understand whether there is one or multiple channels in that specific time slot that is free, so where the radar can transmit. So we designed a radar system with two different chains. One is dedicated to the sensing of the environment, and the other one is dedicated to all the mission of the radar, so the detection and so on. So there is a system that senses the environment, changing the frequency on different bandwidth. And you see here that we have the spectrum reconstruction, or CS, because it is the compressive sensing. This is explained from the hardware point of view, because if you want to reconstruct the occupancy of the spectrum, then you need, since the bandwidth that you are scanning is very large, you need very fast sampling systems. And this is very costly for the radar itself. So we decided to use the compressive sensing technology, because in this way you need only few samples, much less than the Nyquist theorem requests, to reconstruct the spectrum. This is because actually you don't need to know exactly the value of the power in that specific channel. You need to understand whether the channel is occupied or not. So actually you need an information that is less strict than the real shape of the spectrum itself. Then we model this channel with the Markov hidden models, and then using the detection, so the occupancy detection, then we are able to update the parameters of this channel. Of course, the model of the channel are for the communication systems. And we use the Baum-Welch method, that is a classical method to estimate the parameter of a hidden Markov model. Then what we do, based on this model of the channel, we are able to estimate the probability of occupancy. So it means that in this time instant, I'm able to estimate the probability that in the next time instant, that specific channel is occupied. So we compare this probability with a threshold. If this probability is larger than a threshold, then the radar does not transmit, because it means that very likely the channel will be occupied, otherwise it transmits. So this is the system. As you can understand, actually, this is fully adaptive. It's not really cognitive because it is true that you estimate in an iterative way the parameter of a channel, but you use only the previous estimate of the probability of occupancy to decide what to do, okay? So it's fully adaptive in that sense. And you see here the performance. We have the two probabilities. One, E0 is the probability to lose a spectrum opportunity. It means that the channel actually is empty, but you don't transmit. And the probability to have a collision. So you transmit and the channel is occupied. The blue curve are the two probabilities when you don't use any feedback between the receiver and the transmitter, so there is no any cognition, any adaptivity on transmit. The other two probabilities are when you apply this sensing of the environment. So you see that actually the probability, both the probability of collision and the probability of losing an opportunity, spectrum opportunity, are much lower than in the case in which there is no any cognition. So there are other approaches that I can mention for similar spectrum sensing. Some of them are like this one, fully adaptive, so no learning at all. But there are others that use more information on the environment to learn the decision rule. One of these is the sense, learn, avoid. So it is similar to this one. So it selects the free bandwidth. But this decision rule, so this policy, is learned over time. In my case, the policy is clear. If the probability of having a channel occupied is greater than a threshold, then I don't transmit. So this is a fixed rule. These other systems are able also to learn and change the rule that they use for decision. For detecting the occupancy of the channel, we use the energy detector. That's quite easy. Practically, it measures, it estimates the energy in a specific channel. So it doesn't need any information on the communication signals. It is easy, but it is not that performing. So mainly it cannot differentiate a primary user from other signal sources. There are other ways, feature detector and matched filtering. Feature detector practically for some communication signal is able to extract some peak because the communication signals quite often have the header that is periodic, and then they are able to see this periodicity, and then based on that are able to detect the presence of a communication channel. So that's why they are feature-based. Matched filtering means that you have a filter that is perfectly matched to the signal that has been transmitted by the communication signal, but of course communication system. It means that you need to know perfectly the signal that has been transmitted, so you know a lot of knowledge. So going down, you have a very, very good system, very high performing, but very complex, and they need a lot of information that typically in a radar scenario you don't have. That's why we use the energy detector. That is the easiest to be implemented, and it needs very small information on the target, on the signal that has been transmitted by the communication. Now let's apply something similar, but to the tracking. And you see here cognitive passive radars, passive. So it means that actually there is no any transmitter. Passive radar is a radar that uses the signal that is backscattered from the target, but the signal is not transmitted by the radar, it's transmitted by other systems, for instance, communication systems. So imagine that you have FM radio station, or you have a 4G base station. Then they transmit a signal this signal hit the target, and you have a backscattering. So the radar observes this signal that is backscattered by the target, but actually the signal is not transmitted by the radar itself. So the radar has only the receiver, has not the transmitter. The benefit of this kind of system is clear because they cannot be detected. So if a radar does not transmit, it cannot be detected, okay? So that's why they are used. They are used also for other reasons because they are bistatic, so the transmitter and the receiver are in two different positions, and then they can see some kind of target that the monostatic radars cannot see, okay? So there are multiple reasons, but this is not a talk on passive radars. But what is could sound strange here is that I talked about the cycle, so a feedback between the transmitter and the receiver. But here there is no any transmitter. So where is the cognition? How we can apply the cognition? Actually, in the same environment, in the same scenario, there are multiple transmitters, communication transmitters. Can be 4G, UMTS, can be LTE, can be FM radio station, and each one has a different signal, and then different characteristics. And different characteristics that are not only related to the signal that has been transmitted, but also to the geometry of the system. Let me explain. When a target, let's call baseline, the line between the transmitter and the receiver, when the target crosses the baseline, we lose completely the resolution in terms of range, so in terms of position, and in terms of velocity. So it means that this is a bad geometry. So if we have only a single channel between the transmitter, say FM station, and the receiver, the radar receiver, and the target is crossing the baseline, then we know that in this case, the estimate that we do about the velocity of the target and the range of the target is completely wrong. So we should avoid that situation. Well, if we have multiple channels, so other channels, then maybe we can use other channels. For instance, in a different position, we have another FM station, or we have another 4G station, or whatever it is, then we can use this different channel to estimate the characteristic of the parameters of the target, okay? So this is the idea. Where we apply the cognition, we know the environment, so we know in each specific position which is the best channel that we can use, and then we use this knowledge to choose the optimum channel in our estimation, okay? This is the knowledge. So the knowledge is based on the knowledge of the environment and the best position, the best channel, and then we use it for target purposes. How can we measure the best performance? We use the Kramer-Rao bounds, and then we plot in this scenario that is the harbor or Leghorn. It's quite close to Pisa. So you see that here we have the receiver that is at the Navy Academy, and there are two transmitters that we use, the UMTS, and the other one is an FM station. And that's a big harbor, so there are ships entering and exiting the harbor. Okay, so we want to use the passive radar to track the ships in the harbor. That's what we want to do. Then we have two channels that we could use, the UMTS or the FM, or some kind of merging of the two. But there are scenarios, there are particular positions when the target is crossing the respective baseline where we know that we lose the resolution. So in that position of the target, we don't use this channel to estimate the characteristic parameters of the target itself. You see here a map of the Kramer-Rao bounds for the UMTS. So we have the Kramer-Rao bound on range, the Kramer-Rao bound on velocity, on the entire map of the harbor. The white area is the ground, and all the other is the sea. Okay, and this one are the Kramer-Rao bounds for the FM radio station. So you see here, the FM radio station is here, see? And when the target is in this area, is very close to the baseline between the receiver and the transmitter. So you see that is in red because the Kramer-Rao bounds are quite high. It means that you lose the resolution in range. So you have a very bad estimation of the position of the target. If you look back at the other sensor, because it's here, see the baseline is between this receiver and this transmitter. Only here you see a red spot because the geometry is bad here, but here with this channel you have a good estimation of the range, both range and position. So let me show you the model that we used for tracking this target. The trajectory is the red one. So this is the state equation. So with the usual position and velocity on the Cartesian axis, and then the transition matrix. That this is the noise, the state equation noise, and then the measurement equation. Of course, is not linear because we observe only the position and the Doppler frequency, and then we have the measurement noise. The covariance matrix of the measurement noise depends on the waveform, and this is included in this Fisher matrix here, but it depends also on the geometry that is included in this P matrix, that is the derivative matrix. Actually, we proved that this in an article that is listed at the end in references. So it means that the covariance matrix of the measurement changes with the position of the target in the area. Then it is possible to write the Kramer-Rao bounds with the two terms as a Riccati-like equation. This part depends on the previous time instant. So once you have observed your target, you cannot do anything on this. But this second term depends on the new observation, so on the new channel that you choose in your system. So these are kind of a priori information, previous target state, and this depends on the measurement. So the idea is actually that we can write, when you suppose that the probability of false alarm is equal to 0, the PD is what it is. Then we can write this Riccati-like equation in this way. Practically, this term that depends on the new data can be written as a function of the probability of detection, as a function of the covariance of the noise, and as a function of the geometry of the system. So how we can choose the channel? We choose the channel in order to practically, since the Kramer-Rao bounds are the inverse of the Fisher matrix, we choose the channel, one of the two channels, in order to maximize this term. If we maximize this term, we minimize the inverse. So we minimize the Kramer-Rao bounds, we improve the resolution of the system. And this is exactly what we did here. Actually, we use here the trace of the covariance matrix. Let me show you the performance that are more clear than the theory itself. Then you see here that the blue is when we use only the UMTS, the red when we use the FM, and the green one is when we select the channel in the way you have seen. So the performance of these are the variance of the estimate, the Kramer-Rao bound on X, and the Kramer-Rao bound on the velocity along X. So you see that especially for the X, so for the estimation of the X position of the target, the algorithm that we have selected is provide the best performance, so the best of the best. Okay, so this is use of adaptivity on transmit, actually on choosing the channel. Now let me go to something that is really cognitive. It is this one, in the sense that we are going towards a higher level of cognition. This is again the scheme of the cognitive radar system, with the environment, the receiver, the transmitter, the feedback between the receiver and the transmitter. Now, look at this. This is the reinforcement learning scheme, where you have an agent, and this agent in our case is the radar, practically, that observes the environment. Then, based on the observation, it takes an action. Okay, this action changes the environment. The radar observes again the environment, and based on the goodness of the action that it took, it receives a reward. Okay, so it's something that really happens to the human being itself. So if you do something bad, then you receive some kind of punishment. If you do something good, then you receive a prize, and the reward works exactly in this way. And the reinforcement learning works in this way. So what is the reinforcement learning? Theoretically, so from the theoretical point of view, is a Markov decision process. And it is defined by this tuple here, where S is a set of states in which the environment can stay. A is a set of action that the agent can take. P is the transition probability from one state to the other state after a certain action has been performed, so taken by the system. And then R is a scalar, is a reward that is evaluated after the action is executed. Why we talk about a learning system? Because this map between the state of the environment and the decision that is taken by the system is not fixed. The policy is learned over time. So the system starts working in a certain way, then observing the environment, getting the reward. The system is able to understand which is the best action in that specific state. So it changes the policy. So over time, it converges to the optimum policy, okay? Learning over time. Here, really, there is the cognition, not only the feedback between the transmitter and the receiver, but a real cognition. So just to say a few words to explain, imagine that you have a robot that has to go from one point to the other point, and it can take multiple actions. Then you give a positive reward when it takes an action that makes the robot go forward without falling, okay? If to the action that makes the robot fall down, then you give a negative reward. After a certain time, the robot learns how to go from point A to point B without falling, okay? Through the reinforcement learning. This is the technique. So we applied this technique to a massive MIMO radar. What is a massive MIMO radar? Radar that has a virtual array that is very large. Virtual array doesn't mean that you have many massive number of elements on transmit and a massive number of elements on receive. Because if you design a proper way the antenna on receive and on transmit, then the number of virtual elements is the product between the two. So it means that you can obtain a massive MIMO system with a reasonable number of elements on transmit and on receive. So when I talk about massive MIMO, means that the number of virtual elements is very high. Okay, so look here what we receive. Suppose that this is the signal that we receive. This is the target plus the clutter. L is the Elgon bin, so we divide all the field of view in different, very broad angle bins, actually. And then you receive the number of targets, this target signal at the k time instant. What is H? H is the virtual steering vector. So you see that is the steering vector of the transmitter, the steering vector of the receiver, and there is also this W. These are weight matrix that introduces the correlation in the transmitted waveforms. This correlation matrix is used to steer the beam pattern of the system towards the direction in which we expect to see the targets. Why? Because we want to save energy. So if you transmit energy in all the directions the same way, then the signal to noise ratio that you get from each signal is very low. If we transmit high power in a specific direction, then the signal to noise ratio in that direction on that target is higher. Okay? So we want to shape the pattern of the antenna, the virtual antenna, in order to improve the detection of the target itself. So this is something that is not related to the cognition, but we proved that with a massive MIMO radars, so with many virtual elements in the antenna, the probability of false alarm does not depend on the probability density function of the clutter, provided that the correlation of the clutter, spatial correlation of the clutter, decays in a polynomial way. But you can find the details of this part on the article on the massive MIMO radar that we published. So let me explain better the cognitive part. So this is the detector. Actually, it's not a Norman Pearson detector. It's a wall type detector. You see H, the steering vector, virtual steering vector, the covariance, the estimation, the estimate of the covariance matrix. Well, the number of antennas, virtual antenna, is very high. This wall type test converge in distribution to a chi-squared. So the probability of false alarm does not depend on the probability density function of the clutter. Of course, the probability of detection depends on the steering vector, so it depends also on the covariance matrix of the noise, but it depends on the covariance matrix of the signals. So it depends on the steering vector, the virtual steering vector. So the idea is that, well, let's design this matrix W in order to steer the pattern in the direction where the target are expected. So where is the cognition? The cognition is that you don't react in the next time instant based on the knowledge that we have on the previous time instant, but you learn over time how these detections are relating to the real position of the target in the environment. Let me go fast because I'm running out of time, and this is the algorithm that we used to optimize W, so the covariance the weight matrix of the transmitted waveforms, so in order to steer the beam pattern, okay? But we don't know the number of targets, we don't know where the targets are, okay? So the cognitive algorithm, the reinforcement learning, is able to learn how many targets there are in the scene and where the targets are. Through what? Through the reinforcement, through the rewards. The rewards has a positive term that depends on the probability of detection in the angle beam where the targets are, and the penalty that depends on the probability of detection where the target are not. Okay? There are multiple ways of using the rewards. There are no recipes for that. So we could use something that is cap the reward or the signal to interference ratio or whatever. So we decided to use this, and it seems to work. So everything of the reinforcement learning is based on the learning itself that can be applied in different ways. We use the Q-learning through the SARSA, state action, reward, state action. It means that you use this state action value function Q that is updated at each observation in order to choose the best action. Practically, you choose, when you stay in the state S, you choose the action A, K plus 1, that has the maximum of this Q function. You have a kind of table, and you initialize Q generally with the identity matrix, and then you start learning from the environment through the reward. And then you update the values of this Q function over time. And then if you, after some time, after some observation, then you converge and you choose the action where you have the highest value of the state action function. There is another, and this is actually summarized here. So you initialize first the waveforms. You first transmit orthogonal waveforms, then you get some observation, you initialize the Q matrix, and then you start your processing of learning. So given the action AK, you observe this, you apply again the Wald test, then you detect a certain number of targets. Based on this, you receive a reward, and then you choose the next action, which is the next action. Number of targets, the number of targets that you have, and then you focus the pattern in that direction. And actually we use an epsilon greedy algorithm. What does it mean? It means that you don't choose every time the action with the best Q function, so the optimum one. You choose the optimum one with a probability that is 1 minus epsilon. With a probability that is equal to epsilon, so it is low, then you randomly choose another action. Why you do that? Because it is possible that over time you have not experienced all the possible options. If you every time choose the best action, the best so far for what you have experienced, it is possible that you lose something. Then sometimes you choose randomly another action, and maybe you get a reward that is higher than the rewards that you got previously. Okay, so imagine it's the same as that happens in human life. Okay, sometimes you decide based on an experience, and you know that in that situation, that is the best action that you need to do. Okay, because you get the best reward. Sometimes you do something different because we want to experience something different. It can be a mistake, so maybe you got a penalty, but maybe it's the best action of your life, and then you get a very high reward. So the reinforcement learning with the epsilon greedy policy is exactly this way. Okay, now I'll show you the results. I think that the one of these one, you see that this is the probability of detection between 0 and 1. This is the clutter spectrum, spatial clutter spectrum. You see that there are 4 targets, the dotted lines with different signal-to-noise ratio. And this is the classical signal that doesn't learn anything. And then you see that the probability of detection, this is the classical one, and you see that the probability of detection over time doesn't change. okay? Because the system is not learning anything. But if you look here, then specifically for the targets with the lowest signal-to-noise ratio, the probability of detection increases over time because the system is learning where the targets are and the number of targets. And then we compare this with this performance. See here, the black curve is the adaptive. Adaptive means that you use only the information in the previous state. So you detect that in this time instant, you detect 3 targets, and then you focus the beams on that specific 3 targets. This is adaptive. The cognitive systems use the information learned from the previous stage, so it's able also to understand that even though in this time instant you detected 3 targets, maybe there are 4, or maybe there are 2, okay? So the cognitive system is able also to focus more or less target in different positions. And you see that specifically for the signal-to-noise ratio, for the target with very low signal-to-noise ratio, you observe a very high increase in the probability of detection as a function of the number of antennas with a learning with a cognitive system. The adaptive system, practically the fully adaptive system, is almost the same as the non-adaptive or receive, so non-cognitive system at all. So you see that actually the learning here is quite important. Unfortunately, I have to skip a lot of figures in different scenarios where we changed also the parameters, but I can give you the slides so you will, or the references of the articles. But let me summarize about cognition in radar systems. So radar systems are very sensitive systems, and so you need to trust fully your cognition. And this is a clear example that is famous in image processing, where deep learning techniques are applied. So you see that in the first image, your deep learning network is able to classify a panda with almost 60% of confidence. Then to this image, you add a noise, a specific noise. And you see that in the second image, there is this noise, but the human eyes are not able to see that noise. So clearly for us, that's a panda, okay, still a panda. But the deep learning network say that is a gibbon with a probability of 99%. So this very smart noise was able to deceive completely the deep learning network. Of course, there are many papers on that trying to explain why it happens and how to deal with this kind of deception. But in image, it's not a problem in image processing because you have a lot of images, and anyway, panda gibbon is not dangerous. But in a radar application or other sensitive application, you need to trust what you learn. The training time. So the training normally in a cognitive system is based on a trial and errors. So you do a trial, and then you see what you get. Could be a penalty, could be a reward, and then you learn the best policy. And you need generally a lot of data to do it. So can we do this on radar systems? How many data we need to train the system? And most importantly, can we accept that the radar in its infancy makes a lot of mistakes? And how dangerous are these mistakes for a radar system? For an image, I mean, a classification at the beginning is wrong, and we improve it. But in a radar system, can we accept this? And for how long we can accept it? And how can we pass knowledge from one system to the other system? Because the radar systems stay in place for a long time, 20, 30 years. So imagine that you have a radar that has worked for 20 years in a field, and then you need to change it, so to build another radar. How can you pass all the knowledge of the radar, the old radar to the new radar? Should it be on scratch, or there should be some way to select the knowledge? And how can we trust, or can you use all the knowledge, so all the data in the new system where the scenario has changed? So all these questions are very important, and there is not a final response, at least in the domain of the radar. And there is one other aspect that is very important for us, that is the interpretability. So again, in the radar systems, you cannot use black boxes. And generally, deep learning or some of the AI techniques are black boxes, in the sense that you have some input, you have some very nice outputs, a lot of parameters inside, but you don't know exactly what's happening, or at least you don't have an intuitive feeling of what's happening in these black boxes. And for some application, this is dangerous. So interpretability is another very important aspect, and there are groups that are working on that. And we worked also a little bit, but for a different application, not exactly on cognitive radars, but simply on unfolding, so try to understand what a deep learning technique does. And again, there is some reference for that. Practically, there is a way to compare what an iterative optimization algorithm with some prior knowledge does, and a deep neural network does. Practically, it is possible to see that in some cases, the iterations that are performed by the iterative algorithm are comparable to layers in the deep learning networks. In this way, you have an intuition of what the deep learning network is doing. Actually, is repeating, improving the parameters, is repeating iteratively the optimization algorithm. So this comparison between the neural network, the deep neural network, and the iterative algorithm, optimization algorithm, helps in improving from one side the iterative algorithm, and from the other side also the deep learning algorithm, and also to understand what the deep learning algorithm is doing. We apply that in this case for the design of beam pattern. So this is the optimum beam pattern that we want, but the signal that have been transmitted must have a constant modulus constraint that is a very non-convex constraint, of course, so it's not easy to optimize it. Then we compare our technique with multiple techniques in literature, and you see that there is some similarity between this beam pattern and that beam pattern, but with our technique, this is what we get. So practically improving the deep neural networks, comparing the deep neural networks with the iterative algorithm that is necessary to solve this non-convex, relaxed optimization. Okay? So these are by co-workers, people that still in my university, former students, colleagues around the world, and from US, China, and also Germany, Italy. And these are the references of some of the papers that we published and the project that we had. Some is still ongoing, new one, project and grants on this topic. That's it.
So thank you very much for the wonderful talk. So we have one very important part left. First, I'd like to invite Ms. Nimala to the stage to hand over a plaque to the speaker. this is a IISc book called The Secret Lives. So it's a
Nice.
pleasure to give it to you.
Thanks.
Right? Then the owl is here. All right.
Yes, you'd like to see it.
Lovely.
Thank you for coming and thank you for inviting me here. It's a pleasure.
Yeah, so it's my pleasure to close the session today. So first of all, thanks again to Maria a lot for the wonderful talk. Thanks to Ms. Namla for making this DVP happen. And we'll be having 2 such, I think, lectures every year. So please do attend. The third is thanks to all the staff for helping out with all the arrangements. And I'd be amiss in not thanking Hari for actually doing all the hard work, all the logistics, contacting the speaker and doing everything. So thanks, Hari. And thanks to all of you for coming.